I'm very honored today to introduce Professor Jeff Wu, and he specifically told me that don't say anything, because if you read through that, it will take more than 10 minutes. But I'll just quickly saying that Professor Jeff Wu is a chair professor in Georgia Tech in the statistics group, and then he got the COPS President Award in quite early year. And then he also an NAE member in US, the National Academy of Engineering. Something interesting is that I'm not sure he's the only one, but he's the first statistician, I think, NAE, so that's kind of unusual. And the other thing worth mentioning is that because our university, there are 5 important themes for our 25-year anniversary. The data science, everybody talk about it. And if you go to the Wikipedia, search the data science, you'll see Professor Jeff Wu's name come out. He actually is the first one to icon the name data science. So in case you don't know, you could do some Google search. Okay, I think that's a very short introduction. Without further ado, let's welcome Professor Jeff Wu.
Okay, make sure you can hear me in the back and no echo. Okay, thank you. And I like this short introduction. I know once I was in China and they read 1.5 page. I got so bored in like 15 minutes. So I told people don't do that because you cut into my talk. Okay. Last year when I was here, I gave a talk on quality technology, but actually intellectual work of mine since I moved to Georgia Tech in 2003, it took a while. When you move into a new area, it takes a while to see the fruits. And the one big area that I've been interested in, not just myself, all my research team, my former students, is into something called computer experiments. And but computer experiment is a terminology that we use in statistics. In applied mathematics, they call it uncertainty quantification. Okay, so this talk, there are 2 talks. I'm going to give an overview about UQ, and so that's the first part. So if you are an applied mathematician with some interest in UQ, or you would get some sense. But then, of course, I'm a statistician, so I'm going to go into one class of problem called multi-fidelity computer experiment or multi-fidelity simulation. The 2 names are the same thing. And so there I'm going into real research and some design problems, design experiment. And Ray Tor, he's very young, but he has done major work already. He would do the second one and focus on calibration problem. These are 2 major classes, not the only one. Inverse problem is another one. Would be called calibration problem. And you do work on both the mathematics and the statistics. Okay. Computer experiment is all over, is omnipresent, especially in the last 10, 15 years for obvious reasons that it's much easier to do computational modeling. This can be finite element, finite volume. If you are an operation research person, these can be discrete event simulation, like transportation, or network flow, or social network. Or you do computational material design, or design atomic bomb. Okay? The Israeli never detonate a bomb. They done all the computer simulation. I think they have more than 100 bombs, and I'm sure they're very reliable. How? Computer experiment. I hate to say that this is a kind of disruptive, but that's the power of that. But sometimes more than just that, sometimes they are events that so the detonation. The events are very rare. For example, mudslide or hurricane, they're very few. But you have a physical observation. But you can run a lot of computer simulation to simulate different scenarios, to give you better understanding. But then those computer output should be validated by the physical. That's a part in Ray's talk called calibration. So you can see the importance. And there are many examples. I guess the most prominent and most impact is aerospace. The reason aerospace is very hard to run simulation. The simulation already reached like the 5th generation jet fighter. In the US, I know. I don't know China because we have to stay away from that. that you reach almost a technical limit, you cannot run simulation. But you can run emulation, that's what we are doing. To emulate a simulator. So they're becoming very hard. But of course, you do mechanical design, you can do that. But this is really the challenge, the utmost challenge. This one and in other area. But for example, biology is also getting hard. Some biological phenomenon, because more and more, you know, the mathematical biology become very hard. And there are some phenomena that are also complicated to simulate. So I can see that this is moving in many different directions. Well, uncertainty quantification, this I take a subset of, and this is mostly written by applied mathematicians. Okay, I'd rather skip some technical detail but give you a story. The original origin, the UQ was pushed by applied mathematicians, not initiated by the academic, by all the national lab in the US. And national lab are very powerful. In applied math, the national lab people, Los Alamos, Lawrence, Oak Ridge, Sandia, they are very powerful. Once, many years ago, they gave a presentation to the Congress about the nuclear waste disposal, and they gave some risk estimate. But the congressman asked, you don't give me just one number. I want you to have a prediction interval. I mean, they didn't use the term, confidence interval, statistical. They realized, hey, they need to do that. So think about how they did originally. Think about your applied. I have some set of partial differential equation to model the dissipation, say, of some contaminants into the soil or underground water. Okay? Well, so let's say I didn't get a solution. But the solution is complicated. But remember, you put a lot of assumption on the input parameter, in the coefficient or the PDEs, the initial condition and boundary condition. So now put some little distribution around that. Then you can see the output solution would be not just one equation, but one function, but a range of functions. That's the origin. But actually, about the same time, when there was a major paper that was published on this, statistician working on that, but not on PDE, called computer experiment. And these two are converging. So now you can see a lot of activities. For example, SciAm has a new journal called SciAm Journal on UQ. Okay. And I think one of the Institute permanent member is a world-leading expert on inverse problem. And inverse problem also UQ, although ours is more from statistical point of view. Okay, so this kind of definition of UQ, but rather I just show you some different subject. Sensitivity analysis, emulation, construction of reduced model mostly in applied math. Sensitivity analysis, another area, for example, in my research lab, I group doing that. Okay, you have a lot of parameters. Say building, I'm working on one building energy simulation. You have 1,000 input parameters, but as a building designer, architect, you know there are only maybe 10, 15 of them are critical. You don't know which one. So you're going to use the building energy consumption, the real data, and run some finite element simulation and identify. So you can see these are very interesting applied problems. Forward propagation. Okay, inverse problem. So for calibration, the second talk will be related to inverse problem. Mine is a forward propagation. His is more backward. But we are not using the same terminology as in applied mathematics. Okay, and there are other types. Okay. Okay, so here's now a way to describe it from the statistical point of view. Okay. So if I run finite element, and if these are very expensive, I use the finite element result, the output as an input for my surrogate model. Surrogate model is either a statistical model or applied mathematical, but it's an approximation. But this approximation has built in a stochastic element. There are two classes, one called Kriging, is a Gaussian process. Another one is called GPC, Generalized Polynomial Chaos Approximation. The two classes. So they are really coming from different angle, and they are kind of converging now. You can see that's very exciting. And then your physical. So you combine that. And then the purpose is either prediction, optimization, or sometimes elicitation, try to understand. So now the same slide, I use the different terminology. So this is my simulator. This is my emulator. And this can also have that. Now, you can do, from emulator, you can do this. Or directly from simulator, you can do UQ. Now, why I mention it? Because sometimes this is, you cannot run all of that. I cannot generate enough simulation, too expensive. A jet fighter, just combustion engine, to be nearly realistic. Once, Georgia Tech is a very strong aerospace, so we collaborating. One simulation would take cluster of the computers, a very fast computer, a lot of capacity, probably matter of weeks. So you cannot do many. So what you need to do is do that and do some emulator. Emulator you can do many. Emulator is an approximation. You can do many of them. An efficient emulator may take a few hours. Okay, and then so you can also use the emulator to do UQ. Okay, now I'm going to do one specific class. So we need to go into some the concrete stuff. And this joint paper is Ray. He's here. His PhD is from Chinese Academy, but he's educated at Georgia Tech. He worked at Georgia Tech with me as graduate student, then returned to China to defend. Okay, and this appeared in Technometrics, and it was also presented in the annual meeting of Statistics under Technometrics. Okay, so we consider computer simulation experiment that involve control variables, tuning parameters, and calibration parameters. So he's going to do calibration. I will not do that. Control variable will be those that affect the output. For the designing, if I design combustion, or I design a material. Material is become very computational, so computational material design. Okay, you talk the material, they'll tell you that. But the moment there's also, the one this paper focuses on is called tuning parameter. So let me explain. Okay, so we run, say, solve PDE. Well, of course, PDE, you need to stop the computation somewhere. You get an approximate solution. So the accuracy of the approximation is determined by the tuning parameter, like mesh density. So think about tuning parameter. It can be mesh density, a grid, the grid size, or in some of the faster and less accurate is using finite difference method rather than finite difference. Sorry, I didn't correct. Step length, and also the number of iterations. This is less used but interesting, so I won't go into that. As the mesh density increases, the numerical accuracy improved, while the computational costs go up. So now here's an interesting scientific or practical question. I can run some lower fidelity computer experiment. Why? I can run many. Because the grid size is larger, more coarse. Why larger is important? Remember, I'm exploring the design space. I'm looking for a better combustion performance, a better material. So if I run all the expensive one, I can only say I can only afford 10. I do the lower fidelity, I can run 200. But I still need to run some number of high fidelity experiments, and the two combined. So obviously that's interesting. Then the question is, if I build an emulator, how do I combine the two? And that's the purpose of this work. So I said that, and this is what I expect. So this will be, say, a 2D mesh, and these are very coarse, or you get a final one. Final one will be very expensive. So now let's pose a question. This actually was the original problem, and this was done at the Chinese Academy. So they do some very practical work. Shrinkage defects, and this was a practical problem they factory brought to our research center at Chinese Academy under Professor Deng Yu. Okay, so they were concerned about the casting strength because when there are defects, then casting strength is low, and there's a problem. If these materials are used, especially in the very high precision, like acetylite or some other things, or very expensive machining, then they're worried because the whole thing will break down. So they can run computer simulation. What they do is they can use something called the Niyama criterion. and it's a Japanese scientist. And you can run that, and there will be some kind of output, like an image. The image where there's a color, so when there's a purple color, meaning its defects. I mean, this itself takes some material science work, and we have to piggyback on their work. Okay, so these are the weakness, the purple color. Okay, so we run simulation. Then you can run higher resolution and lower resolution, or NIAMA. Okay, how to combine. So I'm going to now develop methodology and later show that going back to the original data, it's real data, to show how this works. Okay, so the formulation is to develop statistical emulator by integrating the simulation output with different real value tuning parameters. It doesn't have to be mesh, any tuning parameter will do. Well, so first we need to understand the relationship between numerical error and tuning parameters. That is, you have to understand, you need to know something about numerical analysis that will help you to build a statistical model, okay, and find out what's available, and then construct a new method. Okay, so first of all let's review. This is a now very famous paper, many citations. And many citations actually are in engineering. I look at a lot of citations, the candidate or taken by engineer, by people who use the method. Okay, so suppose we have a different level of accuracy of different computer codes at different level. And they don't have, it's very general. This may involve different computational mode. They don't have to be the same. Well, so they propose an autoregressive scheme. And so this from the low resolution move to high resolution, or low accurate to high accurate. But remember, there's a difference. The innovation called innovation delta t is so in beginning, the lowest level, the result, the output is viewed as a Gaussian process. This is a standard way of doing in Kriging. So I will not have time to give you a tutorial. Let's just assume that. And of course, this type of tool, Kriging, reproducing kernel Hilbert space, and Ray's talk show a lot more mathematics. They're using machine learning. But in this area, slightly different tool and mathematics are being used. But this delta t should be an independent realization of another Gaussian process. So the mathematical elements are typical sort of Kriging, okay? Now, for our work, and I should say Ray is the first author. That was part of the thesis that he did, not just like a typical PhD student. He was in the driver's seat. I will help him more in making it into a very good product, and also say what's good, what's not so good. But the core idea is done by him, single-handedly. Okay. This modeling approach cannot be efficient if there's a single parameter that underlie the different level of fidelity. I mean, not all the multi-fidelity of this type. For example, if one use a computational fluid dynamics, another use a heat transfer, then they are different. So you cannot say they have the underlying the same. But suppose I run the same finite element, but a grid is different. Only that. The same physics, same computation. Okay, and they are common too. So this is a special class. In the case, you can see that this will not be very efficient. So I want to share that with a lot of people, especially mathematical statisticians. Many tend to think, actually, this went to JASAC, and it's not rejected. They asked really nonsensical question about you need asymptotic convergence consistent. I told Ray, hell with that, we should send to technometric. Because he didn't understand. In this case, it's not that. You have to use your scientific understanding. You see, it's not like prove something. Because model 1 and model 2 are different. You cannot have a common proof. Some mathematicians don't understand science. They only ask that. You cannot fight with them. So I gave up. So look at here. You should understand is that this case using autoregressive, but it didn't take advantage of the commonality. If I have the same thing that they underlie all of them, I can do better on the next slide. So now let's set the, So we have physical model, a set of differential PDE, and we done a numerical solution. And I'm going to skip all this because of time. So exact solution, approximation, error. This. Now x is the vector input variables. It's like in regression analysis would be the regression variables. But the additional one is a tuning parameter. Tuning parameter is a non-stationary. Basically, I should get a term to you right now. Okay? Now, xi is the computer output, is an approximate solution. Remember, typical is x, but here we are into numerical sort. So here another input parameter, the tuning. Okay, so now I have this model. So xixt is the output, and remember this is an exact solution. That is, if the grid, if fidelity is perfect, meaning my grid size go to infinity, go to 0, which is unrealistic, then you get phi x. Otherwise, you have the error, the delta xt. Okay, so in delta xt, before we do statistical model, we should understand applied math. And from applied math, we're going to use that. So as t go to 0, delta xt go to 0. Why is this important? Think about that. That means if I'm going to run a statistical model, the model as a function of t is not stationary. This is a key observation. Very important. And you're going to see where it's different. So I try for young people, I try to explain to you, not everything is improved. Some of the great ideas are not. Not everything can be proved if you really know the philosophy of statistics. Okay. So now we're going to put non-stationary Gaussian process model. Okay, so assume the exact solution and the error structure are realization of two independent Gaussian processes. And phi x is a stationary GP. Okay, so independent, this is like semi-Kennedy or Hagen, but this is a new one. The error structure, the delta xt is a Gaussian process, but its variance is a function of t. And usually in statistics, you want a simple model. You know, this is called the principle of parsimony. This principle, not just statistics, you go to physics. You take the first physics class. You know, look at all the famous laws are very simple. The same philosophy works in statistics. Only the very simple statistical model will stay on forever and be remembered. If you're very, very complicated, I guarantee you, after some number of years, you'll be forgotten. Okay. So we do a polynomial, a monomial, but the same mathematics for any increasing function. It doesn't matter. It's just for the sake of simplicity. And then you should, so the model choice, the L, the one L. The one way to do that, this only works in the case of PDE. If I do a discrete event simulation, there's no mathematics, no underlying physics. But usually in PDE, depends on what you solve. And then you have the numerical analysis will give you an upper bound. And the upper bound is some power function or the t, or the mesh. Okay, so match that with, if I do a statistical approximation, which will give you a probability statement. So I take, say, 3 sigma. Then you map the 2. Then L is 2S. So right away, we can choose L based on the knowledge. So remember, the choice of modeling parameter in statistics is by knowledge, not by data. I mean, when I was young, I believe everything was data-driven. When I got older, you realize a good statistical model is both data-driven combined with knowledge. Okay. I mean, Bayesian in some way like that, but Bayesian within all data is not. It's only when you choose a prior you make. But knowledge-driven goes way beyond your Bayesian. It's like you know your neighbor, you know something about your neighbor you don't like. You walk around the neighbor. That's your knowledge. Okay? But maybe partly data. You observe data, they find whatever they sneaky, that's data. But you forgot the detail. But the detail convert into knowledge. The knowledge of my neighbor, I better avoid him. That's knowledge. Okay? So knowledge and data. So for example, just quick, for example, if I solve differential equation, first order derivative only, I use the H1 space. Then it's function of t. If I do L2 without a derivative, it's L squared. And there are many others. So it depends on, and this is usually available in numerical analysis. So they will determine the L. But of course, you have a lot of data. L can be determined by MCMC also, our next. Okay, so now we propose two major versions of covariance structure. Let's do this one. So remember, the error is a function of input variable plus a tuning, and we need to separate them. So this part, K5, is a very standard one in Kriging or spatial. If you do spatial statistics, the same. It's a covariance function, and that's stationary. Say power exponential or others. But is this the part? It's a new part. This is a Brownian motion. Okay, so between T1 and T2, and this is attractive because the increment is independent. On the other hand, I can do a different version. I can do stationary, stationary, and take a product of the two. Okay, so it depends on where you are. I remember when this was presented in the JSM, Dan Apley from Northwestern Industrial Engineering, who knows a lot of statistics, like the smooth version. And I presented in City University, give a keynote speech, and someone said he liked this one. But my answer is that these are our two children. You choose either one. Doesn't matter. Okay, either general. And of course, there are other, the computation of the MCMC, you can go to paper. It's straightforward. Standard, not straightforward. So Brownian motion is a conditional independent property, but sample pass not smooth. Version 2 smooth sample pass. So it depends on, in some way, this is the same. If I'm solving PD, I know whether it's very rugged or not rugged. Okay, so the knowledge should in some way determine how I choose a covariance structure. And that's what I said here. Okay. Okay, so maybe I would only do one study. The design can skip a lot of parts. Okay, so we use a toy example. And T is a tuning variable. So tuning variable appears here. Okay, and the coefficient are randomly chosen from uniform. These are the details I skipped. So we compare our method, the non-stationary method, with the stationary method. The stationary treating the T as a continuous variable. Let me again pause and remind you. If you treat this stochastic process as stationary in T, obviously it's wrong. Remember, when T becomes smaller, the numerical solution becomes more precise. Namely, variance becomes smaller. So it cannot be stationary. Stationary means that it's constant variance. It's not. So that's kind of a very simple observation. But if you do everything right and you choose a cutting edge problem, then you're immediately famous, basically. So you need to have good, young people always say, hey, I do this, how do I? Well, you may be above your other colleagues. It's because you know how to choose a good problem. And you have a way of thinking outside the box. Okay. So this is stationary. Okay, so stationary, this kind of, but this one, this is good. That is assuming I know it at T0. Remember, this is what I want to predict. T0 is the exact solution. But let's say T.5. And T.5 is because in the original simulation, the best T you can choose, probably I skipped a slide, it's no time. Yeah. That is in the illustration, here, T randomly selected uniform from this interval. So 0.5 is the smallest. So that's realistically you can do. Okay. And I won't go into detail about how it comes. Okay, so we take the average of the integrated standard error, and ours is 0.123, and sorry, the problem, okay, here we compared 3 out of 1,000 and 950 of times non-station the best. Okay. Something big. Array. Why SM0 is the worst in our computation simulation?
It's hard to explain just because it's the wrong model, I think.
Yeah.
Probably because it extrapolated something.
Yeah, something like that. Even math we don't quite. But remember, these do not use all the. Remember, T is randomly, right? This is a simulation. So we use all the data, but you do SM0, you don't take advantage of that. Yeah.
I understand what the meaning of T. What's the variable UNV?
T is, say, T is the tuning parameter, is like mesh density, but it's
UNV. What are the UNV?
UNV with the other design variables.
They're the space grade or?
No space grade, no. For example, this is numerical. This would be, say, my computation material. When I choose it, UNV would be, I want to make the porosity.
Okay, material constants.
Yeah, material properties. Or building energy, like building material. Okay, and that kind of thing. Or I design the size of the room, big or small. Yeah, the engineering design parameter. But we use a toy. Numerical example 2. Actually, so this one we just compare with stationary, that if you didn't do that. But the really gold standard is compared with Kennedy or Hagen because that is available. So this is a very simple Poisson equation with boundary. And of course, it's a toy example we can do. We know the exact solution. In this case, it's a finite difference method. So in this case, the error bound is no. It's because it's finite difference, no derivative. It's the square of the step. So we can choose L. L is 4 because the power is 2. Okay. So now we want to compare the non-stationary method with the autoregressive. The Kennedy or Hagen is major one. Okay. And his second talk also compared with another Kennedy or Hagen. His 2 very famous papers, actually, really famous paper. Okay. So these are simulation. So we have the tuning parameter H. This is a finite difference. There's a design variable. It's just one-dimensional design input, design variable, and H. So the smallest H is 0.005. Okay, and we compare the results. Anyway, because we had the exact solution, we know the result. And look at the root mean square error or mean square error. That our method is half of the autoregressive, about 1/2. Okay, this is to illustrate. And there's a Bayesian posterior. I look at my time. The design part I won't maybe do just small part. How much time I have? About 15, 20?
10, 15 minutes.
Okay. So next part I'll give you, rather I share with you how this led to some new research, but no details. I use picture rather than mathematics. Oh no, not done yet. So back to the casting simulation, I would actually really not into detail. We choose a design called maximum entropy design. And we compare to model. This illustrates how this works. Actually, I didn't get time to talk to you about, even in the paper, we didn't say a lot about MC, but relatively standard. I think the reviewer didn't want you to spend too much space. And we can run posterior like that. But this one doesn't really shed much new light on the science. Not like some other work that I can say, oh, I discovered something. No. Now I want to tell you about design, but I'll focus on some opportunity. That is how people do research. So now, multi-fidelity experiment, how do I do design? The standard way of doing is just called, if I have one fidelity, the very well-known is called space-filling design, like Latin hypercube. Traditional design, so I jump to the bottom, one fidelity is called Latin hypercube. But now we have multi-fidelity. Okay, So now let me denote. Suppose I have only two levels, low and high. Just make it simple. Low fidelity L, high fidelity H. Then I get set of design points for low fidelity and set them for high fidelity. Well, so these are mostly leading work by Peter Chen. Almost all were dominated by him and his student. He created the whole field. The economy meaning that low fidelity, high fidelity should be smaller than low fidelity because they're more expensive. So these are obvious constraints. But nested relationship. You want the design for high fidelity within a subset of low fidelity. Why? Let me pause. This allows you to do statistical validation. I think even applied mathematics would agree. But this thing we can also, not using kriging, we can use another method, which was rated in the CDU, the conference. Here's another paper on its own on applied mathematics approximation. So reason is, suppose I run 5 very expensive simulation. Then I run 40 cheaper one. I want the 5 to be, the location should be the same. Why? I can validate. For example, maybe the low fidelity are really no good. The difference is really big. Then I worry. This gives me a diagnostic. On the other hand, if this for the 5 locations, they are very similar, I can more safely run a lot of low fidelity, cheap simulation over large space. So you need that. And we always need space filling. So to do that, then it's mostly by Peter, and I was co-author in the beginning, called nested space filling design. That you do, there's a smaller space filling design for high fidelity, nested within a larger design for low fidelity. You can use, there are different mathematics, there are a lot of tools. You can, something called nested orthogonal array. Actually, next slide. And so you can do that, but there are a lot of, it's pure combinatorial mathematics or algebra will not do enough. You still need algorithm to spread around. It's like working optimization. Often you need some algorithm too. This is the case. You need to choose a subset carefully with two-dimensional balance. And there are different ways of doing. I mentioned some. They're almost all done by Peter Chen. Peter Chen visited both Chinese U and Hong Kong U of Science and Technology a few years ago. So nested Latin hypercube design. So here's an example. These are the expensive one. These are the cheaper one. So together is this one. So if I run simulation, I'll run the expensive only these 4. But the cheap one, all of them here. So these 4 points, I have both. And you can do this sequentially. And that's another example. Here's another example called convex experiment with qualitative and quantitative factors. Well, because Gaussian process input is continuous variable. But actually, the story is this. He almost defended thesis, but he spent IBM second summer. He came back to tell me, so here's the interesting observation for young people so smart. He said, Gaussian process cannot handle discrete, the qualitative level. But in reality, because IBM he was involved in simulation of big data center. Data center has all kinds of, maybe I had a slide here. No, I did not. Okay, let me just describe. The sum of the input variable are, for example, angle. There are 3 angles. Or say sensor for the data center. 3, 5, 7. That's it. Discrete. So you need to extend the Gaussian process for this to handle both quantitative and discrete input. Okay? So in our joint paper, we have in technometrics, we develop a Gaussian process. Basically, this is more applied math. You need to develop very good correlation structure. It's more a statistical model. Yeah. But you have to develop good ones. And then the next follow-up paper to this is Peter Chen and Zhou Qiang. He's a professor, assistant professor at CDU Industrial Engineering. He's very statistical. He did that major work. So I won't go into this. But what I want to explain is the interplay between model and design. So in the case of when you have a computer experiment, when you run it, you want to choose a design for running a computer experiment with both quantitative and qualitative factors. Then traditional design doesn't work because discrete one only different slices. So he used a slice design. And I was involved because I gave one initial idea. One of my least cited paper, but I remember the value. A least cited paper on response survey methodology for this type. But there I use slicing. I say least cited, but I remember some value there. I mentioned Peter, read the paper. It's there. But sometimes a paper, when it's the wrong time, then you never get cited. There was one idea called the sliced. And of course, this is mostly his work, so he led to a lot of work. And actually he used this slicing one for machine learning. That's really interesting about how he moved things. Slice. Actually he did all machine learning, use this tool to do computation. What I want to say to bring to you is that some of these work are mathematical, nice and esoteric, but they're very applied. These are best research in applied mathematics. Had to be very useful, deep, and still very relevant. So these are some examples of slicing. Because you can see there are 4 slices. So every slice has 3 continuous variables, x1, x2, x3. Just take only a square projection to show you. And, okay. But now you see, sorry, there's a whole design. This one slice, first slice, second, third, fourth. When they put together, it's the previous one, very nice. So you want overall very nice, but for each slice has its own properties. That is driven by the statistical model that I don't have time to explain. So I want to summarize so that, maybe questions. The concept from numerical analysis are introduced to modeling and analysis of computer experiment with different mesh densities. And we developed a non-stationary Quickie model to integrate simulation output. And the results seem to show very good because it's published. I should say, very important, this method, the non-stationary emulator we developed, is generally applicable to any tuning parameter, as long as it satisfies the underlying structure. And next one is there's an interface between modeling and design, like nested design for multi-fidelity modeling and slice design for quantitative and qualitative factors. Thank you.
Is there time any question? Comment?
I have a short question. Is there any result about the convergence speed of?
Can you speak louder?
I want to ask: is there any result about the convergence speed of the your non-stationary Gaussian process?
Okay, the convergence rate usually done in the applied mathematics mode, like you do polynomial approximation, and in the mode there are a lot of results. Ray has his own paper. Can you answer that? You probably better to answer that. But also using kriging, so.
Yeah, in the context of kriging, people don't do it that way. But in applied math, people are using a different concept called some interpolation scheme. For example, kriging is also related to an interpolation method called radial basis function. In that concept, we can derive some convergence rate.
We can translate into a reproducible kernel Hilbert set and do that. So should we write a second paper?
Maybe.
Yeah. You see, this is good. Statisticians and applied math think very differently. And both have virtues. You are more from applied math?
I think I use
Yeah,
both.
yeah. Not in this type. For example, I'll give you an example. Kriging is used in spatial statistics, not communication only. There, again, we don't use the terminology. Yeah. And, well, there are statistical criteria. For example, the Kriging is the best linear unbiased predictor. So basically, that's the best. I'm just saying that. And of course, you can pull some asymptotic, but I think those are not very important. Those are known already, expected. You just spend all the time get it right. Yeah. But if you do, say, GPC, general polynomial chaos approximation, you always do the convergence rate. But I went to science meeting, and some of those convergence rate, I just fell into sleep right there because they're standard. I know you just work hard, you get it. You know it's true. There are two types of asymptotic. Some are very interesting, unexpected. Some are you work hard, it's muscle. So a lot of muscle get a result. Which one you want to do?
But you're using it. You're using the error estimate to do that. To say
yeah, no, that's fine. I use it and do that. But error estimate doesn't have to be that rigorous.
May I ask a question? So
yeah.
The hypothesis you made about how the covariance matrix looks like in terms of the different level of resolutions, like T, you have minimum T1, T2.
Yeah.
What's the insight? Well, why it has to have this?
There is statistical insight, not applied math insight. For example, the Brownian motion. The Brownian motion, because the T is a Brownian motion. So when you move from T3 to T2 to T1, the increment will be independent.
But you're looking at the errors from your numerical solutions, right? Which are dependent on the level.
Yeah, but usually it's Markovian. It's more, T2 affect T1. So T3 is further back, so not affecting. Now, remember, modeling is different from pure math. There's an absolute, modeling is an art in some way, right? For example, why do I do least square regression? Can you say although people can argue it's Gaussian marker. Come on, Gaussian is a trivial result. Gaussian assumes the model is right? So there's difference between statistics. And
I'm just wondering, what makes you to be a better artist?
Yes, there's some great statisticians, mostly good artists. George Box, they will come up with innovative model. Like Gaussian model get Nobel Prize in economics. So you need to have, or Box and Jenkins. That's another 1 hour lecture on the art of modeling. They separate statistics from mathematics. But I would say, one of my slides already explained that we have two versions. One version is very smooth sample pass. Another one is more a very jagged sample pass, but stationary, increment independent. So, and I don't think is there any further insight about our two versions?
Not yet.
Yeah. I think it's because, again, in some ways, the lacking, I think this area really is a confluence of applied math and statistics. For example, if statistics cannot explain, use applied math.
I don't want to take too much of the time, but can you verify those hypotheses? If you run enough number of simulations, can you check how?
Yes, because the residual will be very small. Yes, there's a statistical way. Yeah, residual become very small. Yeah, basically this. Yeah. But of course, in reality, you cannot afford that. But I tell you how they verify. No, the verify is not that. If I work with engineer more than that, there is when they get a good result, they know it's true, and they're smart. You talk about, say, like Georgia Tech, a group doing combustion, and if they get a result, the emulator, because the simulation, usually is experience. My whole career do combustion for 30, 40 years. I have a lot of knowledge, but I can only do so many. If your emulator gets some result, in the region I cannot test, I look at the result. It's very different, I don't believe. Then I run my simulation, and I see a big gap, I say, your emulation no good. Then I need to return and sharpen my pencil. Why? I may need to, there's something lacking in my statistical model. Yeah. So either all within data, like residual, or the more is, we have to do in real world confirmation or validation.
Ask us maybe a stupid question. And is any of the mathematical theory other than the model from the PDE or from you mentioned the Latin type of 2, the theory, general principle, and the mathematical theory to guide for other sub-theories for the statistical models, I think.
Latin cube has been well developed in design experiment, and there are principles. I mentioned a bit about space filling and others, but that will take a while. But Latin cube is, actually, again, Latin cube originally was Los Alamos lab, was doing simulation for nuclear weapon. This is a famous paper. This is like when they done, say, the most important paper in trigonometry in the last 50 years. This is one of them. It first came out, I was young, but I didn't realize it's so important. And the reason is because simulating some nuclear thing was so expensive, so they choose that. So, but this is now well developed in design or experiment on the one hand. The PDE is not ours. It's, remember, I'm only half of the whole thing, the applied math. You talk applied mathematician, they do GPC, but they know a lot more about PDE. Even if they are not the numerical PDE people, they need some knowledge about the behavior or the solution of PDE. It's very important. Otherwise, you get some result and then match the knowledge. So statisticians need to work, if you work on the real world problem is applied math and statistician work together. Because each one is different. For sparse grid is used in applied math to choose a point for simulation. We do Latin hypercube. And there are pros and cons.
In the motivation part of the talk, you mentioned like simulation of a combustion engine, nuclear bombs, and a fighter jet, right? I guess those are very complex systems. But the simulation usually was very, very simple, just say a few variables. So I'm just wondering whether the results you got from the simulation were generalized to those complex systems.
No, of course I cannot say that. Remember, first of all, when you write a paper, you want to write a jet fighter, probably Ray would do that forever. He would never even get a first job appointment. So you need to illustrate. But this paper is a methodology paper. Don't get it wrong. I'm not saying I'm a methodologist. I don't do those things. But for my own, even my own work, a good methodology will be used. For example, Georgia Tech, Dmitry Mavis, he's in aerospace. And his group using a lot of my tools. And I don't want to know what they do because they have all the confidentiality. I don't care. Most of his students will come to take my design experiment and computation class. And I don't want to ask. So you basically they become more development. And you get good code, you need to stabilize. But there are a lot of further work. I should say that you may use parallel computing. And more than that, you have to do numerical solver. You may do QRT composition, and there are other things I don't know. But you should do what you are good at. What I'm good at is I'm a statistician. I can invent some new thing in statistics. I cannot invent new thing in applied math. But I can only tell you, I won't give you the detail. Yes, such method being used. Here's an example. When Peter Chen first got a result, before paper was published, two companies, I remember that, our paper. Boeing and General wrote to him and asked for his code. His code was not a very good code, he's an academic. So they start using his method before the paper appeared in Technometrics. The best testimony that you have a good method. Okay, same with the mesh density. Yeah. But it doesn't mean if we can do everything, we're going to replace the whole aerospace department or material science department. No, we cannot. Yeah. We're working with them.
But I mean, just follow up. Because you try to quantify the uncertainty, right?
Yeah.
Then you go from this small problem you run, right, to
But the theory is not small. Theory is general. It's only illustration. Theory is general. Theory is not two-dimensional. It's any. So it's not true. However, when you do reality, there are other complexity. They take different treatment. So if I were working like when I was younger, on some automotive, some aspect that outside the textbook again led to new research. And I'm sure if we talk again in 3 years, I will present another thing on that. Yeah. But the next talk will show you that there's another complexity.
Okay, thank you.
Yeah.
Probably we take the 5 minutes break and then we'll go back for the next session. It's a 12-hour break. Okay. So let's thank again.